So let's do an example of carrying out this matching for C1 and C2 in a little more detail. And before we carry out matching, we actually have to renormalize the two theories. Well, we've been talking as if the theory above is the standard model, so we'll imagine that we've already renormalized that. And so we only have to renormalize the effective theory in MS bar. So we'll talk about doing that, remind you of doing that, maybe something you've seen before. So there's going to be wave function normalization. CF is 4/3. I'm going to leave out the prefactor, this prefactor. It's always going to be there. I'm going to stop writing it and start just focusing on the thing in square brackets here. We'll do calculations with Feynman gauge. I'm not going to really do the calculations. I'm just going to quote results to you. And in order to simplify what we have to write down, let me define the set of spinors that you get from taking the tree-level matrix element of O1 to be S1 and of O2 to be S2. So this is just the spinors that we wrote down before for the case of S1, exactly what we had before, and then for S2, just a slightly different contraction of color indices. Okay, so that's just trying to make the lowest order result simple to write down, so that when I write down the higher order result, we can focus on the things that are changing and mattering, and not on the complications that come in from what we're talking about. So if we think about diagrams here, we have a 4-quark operator, and we just have to draw all the loop graphs. Right? We have to regulate them in some way, because they are IR divergent. So let's regulate them with, if we really want to talk about the matching, which is what I really want to do eventually, we should regulate them in some way. And so let's regulate them with off-shell momenta on the external lines. And I'll take it to be a common off-shell momenta, P. And I'll just set the masses of the external lines to 0, since they're not going to matter. OK, so then what does it look like? So the matrix element of O1, the 0 means bare, is going to have divergences, and it has the following structure. Times spinor 1. And then there's another piece that involves spinor 1. And then there's a piece that involves spinor 2 that shows up in from these loop graphs. So even though we're calculating the bare matrix element of operator 1, the spinor combination 2 shows up because this is supposed to be a gluon, and the gluon moves the color around. And I'm only writing the divergent terms, so that later on we'll be interested in the constant terms as well. So the dots are the constant terms underneath the logarithms, and all these little round brackets have constant terms in them. Part of the reason for introducing the basis in the way I did is that when I want to quote you the result for O2, it's the same, just switching 1 and 2. And so the statement that you would have from this, these are ultraviolet divergences, the infrared divergences are regulated. The statement that you would have from this is that you can look at these various terms and you can ask, what's going on with those divergences? Well, this one here is actually canceled by wave function renormalization, which I haven't put in yet. And this one here is O1 mixing into O1. So this one here is a counter term, if you like, for O1. And this one here is a counter term for O2. And the language you use is you say that O1, which we're calculating, has mixed into O2. Okay. So there's two different methods where we could use to carry out the renormalization here that are actually equivalent. So method one is called composite operator renormalization. It's useful to know what things are equivalent so that you know what you can get away with ignoring. So what is composite operator renormalization? Well, you think about having a bare operator, and you need to introduce some constants to renormalize. These are not related to wave function renormalization. It's actually operator renormalization. You have multiple fields at the same spacetime point. You need additional renormalization constants. That's what these z's are. When you go to take the matrix element, you have to include the wave function renormalization as well. So the bare matrix element has a wave function renormalization as well as this z. And this is the relation between the renormalized matrix element and the bare one. So this guy here is renormalized and amputated. Okay, so that's the relation. You can calculate O0. That's what we were doing. We just calculated O0. We could remove z psi, and I just told you if you remove z psi, it's going to get rid of this. And then you use the remainder of the stuff to get zij. I'm going to need the other way around, so let me write that. So I can write this relation the other way around, and then it looks like this. OK, so that's one method. The other one is related more to how we usually think about things in terms of gauge theory, and that is to have counterterm coefficients for the various operators. So start with the Hamiltonian, written in terms of bare coefficients and operators that have bare fields, bare operators if you like. And now switch over to renormalized quantities, so you get z psi squared. We have to switch over from the bare coefficient to a normalized one, so let me do that first. So we get some z for the coefficient, some renormalized coefficients. And then we get a z psi squared from the 4 fermions that are in this operator. And we get an O. And then we can write this in terms of CIOI plus z psi squared zijc minus delta ij cjoi. And then this would be our counterterms. So we would stick in this guy. That operator we haven't renormalized. We haven't done our operator renormalization. We're not doing method one. So the matrix elements here will still diverge, but we cancel them off with the counterterms. Okay, so that's the logic of method 2. And once you do that, the divergences cancel between these two terms, and you're left, if you like, or even if you don't, with the coefficients times the operators, which are renormalized, both renormalized. Okay, even renormalized separately. And these two are equivalent. These are equivalent ways of thinking about the same thing. And we can even go further and derive the equivalence of them. So if we take this theory and we take the matrix element of the Hamiltonian in this second way of doing things, what do we get? We get this. So even though it was OI, I said we haven't done operator renormalization, so we still have a divergences there. That's CJ/OJ. And if we write the OJ using the relation at the top of the board, then we get CJ, ZJI inverse, Z psi squared, OI 0. And then we can just look at the two sides. They both have a Z psi squared. They both have a CJ. They both have an OI 0. The only thing that's different is this. So we find that Zij for the coefficient is the transpose of the inverse of the Z's for the operators. So that's a more definite way of saying the two would lead to the same results. And this is how you would actually get the relation between the two ways of doing it. So it's not, completely trivial. You have to know you have to take the inverse and transpose. But it's the same information. OK, so in our example, the Z is a matrix. It starts out as the unit matrix. And in MS bar, we collect the divergences that are not canceled by wave function renormalization. And that gives us this little 2x2 matrix. And from that little 2x2 matrix, we can construct an anomalous dimension for the operators. So let's do that. So how do we do that? Well, if we take the renormalization of the Baire operators, remember those depended on the regulator, but they didn't depend on the scale mu. So if we take mu d by d mu of OI 0, which is the Baire operator, it's 0. That's what I've written. And then we can write O in terms of the Z, an equation I erased. And both Z and the renormalized operator depend on the scale mu. And so that gives us this equation. So I'm doing method 1 here, if you like. We're using the notations from method 1. If I take that equation and rearrange it, I can write it as an anomalous dimension equation for the operator. It says mu d by d mu, which is one of the terms. I isolate this, and I move that over by taking an inverse of it. And I just call everything that I get there the anomalous dimension of the operator. So gamma ji is all the other stuff, which is zjk inverse and I put the explicit minus sign here, so there's no minus sign in that equation. So the anomalous dimension is determined by the z factors. And we determine the z factors, so we can stick this equation into that equation and get the anomalous dimension. when we do that, we have to be careful about the fact that alpha s in d dimensions has a little extra piece that's actually important for this discussion, which is this piece. So when we take mu d by d mu, you ask what depends on mu, and it's the alpha here that depends on mu, and it still depends on epsilon as well in that equation, and so this term is the term that matters at one loop, and this matters at two loops, and so does that, but at one loop we can just replace this by the identity, and we can drop this. Okay, put those things together. Anomalous dimension, of course, is something that doesn't depend on epsilon, and it's, in this case, a 2 by 2 matrix. Okay. And we can solve this problem. If we want to solve this matrix, then what do? Well, you could diagonalize it. That's how you would solve it. So if you want to run the operators in this theory, just for completeness, you would diagonalize by forming O1 plus or minus O2. Call the coefficients of those new operators C plus or minus in an obvious notation. And when you write down anomalous dimension equations for these guys, there's no mixing anymore at one loop. In general, this is a procedure, if you do this diagonalization, that you have to carry out again when you get to two loops. It's not like the basis that you pick at one loop will be fine for two loops. We're not so lucky. But at one loop, this is a perfectly valid basis. The problem. And in a hopefully self-evident notation, I either take all pluses or all minuses. Okay. And if I write my Hamiltonian, I could write it in the original basis. And if I switch to the other basis, I'll set up my conventions so that it's simple. And that means I picked C plus or minus to be C1 plus or minus C2 over 2. Oops, thank you. Yeah, they have the opposite sign. First one's positive. Second one's negative. And in this new basis, tree-level matching, which is your boundary condition for your evolution, is that both coefficients are a half. Okay, so then we could solve the differential equation the same way we were doing for QCD, write down a result that would sum logs below the scale of the W mass. All right, so we'll continue along these lines next time. Say a few more words about renormalization, which is really just a lead up of doing the matching, which is what I want to, kind of the thing I wanted to spend a little more time on. But we'll finish that up also next time and move on to some other things. So there's a few things to emphasize when we do the matching, and I want to write down the matrix elements in the full theory, which are box diagrams. I'll write down the results for those. We'll compare those to the results in the effective theory, and we'll draw some lessons from that. And we'll carry out the matching, figure out what the next order coefficients would be here. What would those order alpha s terms be? What's the procedure I would go through to get those coefficients? Okay, so we'll stop there for today.